time. So welcome everybody. We appreciate the investment of time. Hopefully, this is a fairly neutral class in that we talk about, best practices and gain structure, but then we're going to talk about some of the nuances of how that affects Q-SYS and how we interact with it in the Q-SYS platform a little bit, and some best practices in, this type of such stuff also in Q-SYS as well. So general knowledge with a little bit of specifics on there as well. I'm going to go ahead and share my screen and we'll get started on this guy. And if at any point during this you need to ask a question, please drop those questions in the Q&A. Koi's on, he'll handle those. If need be, he may interrupt me just to get me to, maybe it's a question that's better answered verbally rather than via text. So we'll do that as well too. So let's get started, everybody. So this is a troubleshooting guide of Q-SYS installers with better understanding of gain structure and how to get the best audio performance out of an audio system, and most importantly, a Q-SYS audio system. So we're going to talk about the importance of setting gain structure basis for all audio in the system. And one thing, and you've probably heard this before, I call it the GIGO, the garbage in, garbage out, right? We put bad things in. This isn't a magic box. We can make some things work better and sound better, but there's some things we're going to find they're just a hard limit there. So best practice. One of the things that we're going to look at here is just proper gain structure is probably the most key component in getting the best audio performance out of your system. Many times, in the past, as an integrator, someone would send me their file and I'm having trouble with this, and you look and like the levels of everything coming in or at different levels, and you get to like the matrix mixer in the middle, and there's a lot of manipulation of signals there. We're going to talk about how, if we start at the front and we do our due diligence through all the way to the end signal going out to the output devices, how that's going to benefit us. But the first thing we have to do is we have to talk about some of the terms and some of the language associated with this, right? So review, let's just go through a review of some of these terms, right? So you're going to see here that this meter that we're talking about that is on the slide here is in dBu. So dBu is dB, decibels, referenced to 0.775 volts, or an RMS value of 1 volt, right? So every dB itself has to be referenced to something. So in this case, it's a dB. When you see dBu, which is what you typically would see on old analog audio meters and things like that, it's referenced back to the RMS value of 1 volt. So it's that 24 plus 24 dBu is pretty much the industry standard for a clipping point for all professional audio devices. What you will see is what you'll find out is you can't pass a signal that's bigger than the power supply of the circuit that you're feeding the signal into, right? So what happens when you overdrive, when you go over that, it's called clipping, right? So the clipping point in this circuitry is going to be at plus 24 dBu. Clipping is when you have an input voltage that's higher than the maximum output voltage of the power supply. So the incoming sine wave is much larger, and what happens is it gets truncated or clipped down to make the wave fit. There's where the term clipping comes in. So this is also can sometimes be called distortion or overdriving. Very cool if you're a rock guitarist, you're going to want to clip and overdrive your signal, and then in later stages down, that's done typically, if anybody's curious, on guitar amplifiers, you overdrive the input gain stage, and then later down on the main amplifier stage, you turn the volume down to control the overall volume, and you get your clipping there. So clipping in audio conferencing, however, and distortion is not something we typically look for. And so much of this is conferencing based. We're going to stay focused on that. But every analog device has some kind of noise associated with it, and that's understood, right? So what we're showing here, this little chart is actually an example from our CML4 cards. So the clipping max input level on a CML4 is plus 27 dBu. The max noise floor, or max 24 dBu, plus 24 dBu. Now you'll notice that the noise floor that we publish for that card is at negative 81. So meaning when nothing is plugged into it, just whatever it is actually, the noise generated inside the circuitry is at negative 81 dBu. So that therefore means that if we look over at the slide deck, or that we have the difference between negative 81 dBu and plus 24 dBu is 105 dB. So that is stated as the dynamic range, right? So the dynamic range is how much you have between the noise floor of the input and the clipping point at the top. Headroom. So in general, it takes 10 dB increase in SPL to be perceived as twice as loud. What we like to do ideally is we want the signal to noise, our audio to have a 20 dB of headroom in the signal that we're reproducing. So therefore, what you will typically see is we'll set a nominal level 20 dB down from that. When our scale is dBu, that's going to be plus 4 dBu. So on your old analog meters and stuff like that, that typically is that point where it starts to turn red as you move in. A lot of people say we're setting for 0 dB or we're normalizing all of our inputs. Typically at plus 4 dBu is where you're going to be on that. So signal to noise ratio is actually is the level of the input signal above the noise. So when we set this level at plus 4 dBu, what we actually are doing there is the signal to noise ratio is the difference between the noise floor and our nominal value that we've set our inputs at, right? So in this case, we have 85 dBu of noise floor, right? Because negative 81 to 0 is 81 plus 4 more is 85. So that's what, and we want, we want our input signal to be sufficiently above that noise floor. So the nominal level that's kind of drawn out there is the sweet spot that allows the headroom to be able to, and also maintains the best signal to noise ratio. Like I said before, in professional audio signals, line level, our plus 4 dBu is nominal. Consumer, you will see, is can be negative 10 dBV or negative 7.7 dBu nominal. So those come in just a little bit lower, about 15 dB. Let's see, 4, 11, about 12 dB lower than that. So that's why typically when you come in out of unbalanced outputs out of a consumer device, you may have to give it some dB of gain to be able to get it to that nominal level. Microphones, we typically will say are around a negative 60 dBV or negative 57.8 dBu, but there really is no standard microphone value, right? For condenser microphones, as their levels will vary quite frequently. So that will be microphone dependent, but just a standard dynamic mic, about 60 dB down, it's where it's looking at. So the preamp, this is preamp. When we talk about preamp circuits, this is the place where we have to take the signal that we have and we have to bring it up to a specific level. And then we present that to the analog to digital converter, and then we go into the digital domain. So this is important. So we add the signal, we add a gain as needed to match the level we want to sample at before reaching the digital domain. So every DSP on the market uses some sort of analog preamp circuitry, right? Because that we have to do that. We have to take it from the analog world into digital. And then on the backside, if we're going out to an analog device, we go back from digital back to analog. But once in the digital space, gain is just a number at that point. Since Q-SYS is not a floating point, we can scale up and down once it is in the digital in Q-SYS. So, but we have to have a nice clean signal at the analog to digital conversion, or it's going to be dirty throughout the chain there. So, your input device, if I'm bringing in a microphone, for instance, and it's at, I need to add maybe 60 dB of gain to get that up to where I need it to be. And then we present that signal to the analog to digital conversion to get the best sample we can. Now, here's where it becomes, this is an important thing in Q-SYS. So when you look at most meters in Q-SYS on the input side are going to be in DBFS. And DBFS is dB full scale. It's actually, once you get into the digital domain, you no longer reference back to the 1 volt RMS 0.775 like you do in DBU. This is actually based on where is the clipping point in the digital value, right? So wherever the top value is, that's where our clipping point then will be 0 dB full scale. So you can understand where if people have typically been used to some of the other DSPs out there, will actually allow you to put, you set all your inputs to 0. If you do that in Q-SYS, you're going to be setting all your inputs to clipping point. So you just want to make sure, be aware that how the meters are labeled there. So what you're actually going to shoot for to give you that 20 dB of headroom is all your input levels are going to be set to -20 dB full scale. And that's an important part. So we want to allow the headroom. So simply add preamp gain to each to reach -20 dB full scale. That's what we'll do. And we're going to do that for every input in the system. Now I know, and you do that by manipulating, as you can see on the chart here, the preamp gain itself. So your signal flow on this would actually be, you're coming in, you're going through this gain. This meter is in dB full scale, which is after this meter. And then any changes you made in the digital realm would be after the analog to digital conversion. So that's kind of how that input block works there. Microphones are a little different situation, right? Because they have their own noise floor. So when we go back to, we go back a couple slides here, well, our noise floor, might be the output without plugging a microphone in, it's going to have whatever the circuitry's noise is. But when we bring a microphone into the mixture, now that noise floor varies, right? Because it's a piece of equipment, it's going to have its own noise, but also microphones inherently grab noise from around the room and things like that, especially with the trend we've been having, over the last, I say trend, it's been a good, 5 to 7 years that we've moved to a lot of ceiling mics as the technology's gotten better, but they typically can bring more ambient noise of the room in. Even a microphone in your hand or a microphone, gooseneck microphone on a table will bring some of that in too. So what we'll do there is you'll simply add the preamp gain. You want to do that for every input in the system. And that's important. Like a lot of times people will, set the unity gain or set nominal levels for all the microphones, but then say if they have a third-party device coming in, whether that's an old hard codec or something like that, if it's a VoIP line coming in, if it's a POTS line, all of those inputs need to be at the same nominal level, -20 DBFS, to be able to do that, so that we're accurately treating all of our signals the same. So one thing to know though is there's no way to fix poor signal to noise ratio at the mic with the DSP, right? So our AEC algorithm does, what we want to do is we want to have at least 15 dB of intelligibility. That's the AVIXA standard for speech intelligibility. So if I'm at my nominal level is at -20, I'm going to want to be at least at -35. So, but the idea here is there is noise reduction, you'll notice in the AEC algorithms, but that is really just to get rid of steady state and constant type noise. It's not really it's not there to get rid of, just ambient noise into the microphone itself or circuitry based noise. So if I'm looking at this signal and my standard, like I'm not touching anything, just the ambient noise coming into the microphone is at -31. Well, then I only have 11 dB. And so this would not meet the 15 dB of minimum signal to noise ratio for speech intelligibility. Easy for me to say this morning. Maybe I should have a drink. So if we look at that now, this would be, right? So if I've got a microphone plugged in and just the ambient noise, I'm quiet in the room. If I've set my nominal level when I'm speaking into the microphone at -20 dB full scale. And then when I stop talking, as long as that drops below -35, we're good. So best way to test, have a talker, start talking at microphone in normal distance. And, obviously we've all set the conference rooms up perfectly with the microphone right in front of our face. And then when people use it, they lean back and do all of this. And we understand that some of that's training. But the idea is you get a nominal distance from the microphone. You, while someone's talking, you raise the input gain up, adjust the preamp input gain up until the level reaches -20, then have the person stop talking. The peak level when the person is silent should be at least -35 dB below. And then if the signal is greater than 35 when the talker is silent, we're not meeting that intelligibility thing. You may have to treat the room, you may have to have an uncomfortable conversation that this isn't the best room for conferencing, or address, microphones, things like that. So poor signal to noise ratio must be addressed at the source. So just something I can't stress enough. Let's go in, and if we take a look here, what's in a typical microphone signal path? So if we bring a microphone into our signal, typically you'll see, now I will say this, I just want to throw out as a disclaimer, I've always said that DSP work is kind of like, artwork. If I told everybody on this call to, draw a car, they may not all draw the same make, model, and year. But if in the end it gets you from point A to point B, you've still drawn a car. So, this is common practice suggestions. You may have found better practices at work, but typically what you'll see in a microphone signal pass is a high pass filter, a parametric, and a low pass filter. In the high pass, we will roll off the cutoff frequency around 60 to 80 hertz. The human voice doesn't get really down that low. And you can use any type or any slope for that. We're fine with that. And then the parametric EQ, what you do with that one is you typically will use it to notch out any problematic frequencies that the microphone might be experiencing in the space that it's in. And then on the back side of that, you'll put a low pass filter. So somewhere around 16 kilohertz, you could go as low as 8 kilohertz if you needed to, if there's just some type of other high frequency energy in the room that you want to try to eliminate, you can kind of lower that down. But so that's kind of the typical signal path. Now I've seen people not use a high pass and a low pass and put a 5 or a 7 band parametric in and use the parametric to do some of that. That works too. If it sounds good on the other end, you've done your job right. So it's kind of like programming. If the system works and works reliably, it's been done right. How you got there is your business. So, but what you would do there is on setting the parametric up is you consult the microphone manufacturer for their recommended curves, because nobody, just like flat loudspeakers, nobody builds a perfectly accurately reproducing microphone. So they're going to have some recommendations in there. I know for a fact, like the Clear One little teardrop tri-element mics from 7, 8, 9, 10 years ago they recommended a little bump actually in the vocal range to kind of get some clarity in there. They actually included it in their design, and then they took it out later. And so just something to be aware of. So check your microphone manufacturer and look at the curves that they recommend, because you're going to want to do that so that you can add that to your parametric. What you want to do is you want to have separate microphone EQ away from your room EQ, right? Because you may have different microphones that are facing different ways in the room, or they're having different reflections based on where they're placed at in the space. And then on the output side, you may want to you'll want to add some equalization for that. So emphasize your frequencies if needed. So your vowels are going to be between 250 and 1,000 hertz. Your consonants will be between 1,500 and 6,000. And then your sibilants, S's, T's, and Z sounds will come in between 5,000 and 8,000 hertz. So something, just kind of know that, right? Because if someone's, losing some intelligibility, I do know that on phone calls, it's funny. For some reason, my S's, my last name is Waltins, people will put an F instead of that. And I'm just thinking like, well, maybe some phone systems don't quite get into that 5 to 8K range very well, right? So could be why, people say, your name is WALTENF. No, it's S. So anyway, something to think about. Identifying feedback frequencies, right? So what we'll do there, what you can do is add a notch feedback controller. So this is a Q-SYS product, and then you're going to make some noise. So this is an ad hoc way to identify the room modes for an integrator that doesn't have any analysis tools, right? So you can use that. This exercise here would assume that you are doing sound reinforcement, right? The microphones aren't going to a conferencing end. This is just a basic sound reinforcement type setup. So what you would do is you would just take a microphone that's in the system and add the notch feedback controller in there. It's going to listen, and it's just going to eliminate feedback for you. So you'd set your, I'm going to go to this next slide and we'll kind of talk about it here. So with the notch feedback controller, when you open that component up, you'll see that you've got clear all. So you've got filters there. This will clear all your filters. This will clear just the dynamics. When you bring this into your design, you can actually, when you bring this into your design, you can determine, I can have up to 32 filters in it. I will tell you, if you drop 32 notches, no matter how thin they are, into a vocal range, you're going to, it's going to sound like you're inside of a can. So I typically will eliminate these back to, I'll set them to a max filter count of 8, maybe 12 or 16. But you can also put it between how many fixed filters you want and how many dynamic filters. Fixed filters will be put in place before the dynamic filters, and they will not change. So those will stay there all the time. The dynamic filters based on when the what the time is set to. The on the far right over here is the reclaim time. So once that feedback condition doesn't exist, if you have that reclaim time set like this for 30 seconds, is over 30 seconds, it will start pulling that dynamic filter back out. But the idea of what you'll use here is you'll talk into the microphone, and you'll see that you have, this will help you identify that you have problem frequencies at around 150 to 210 hertz and from 600 to 800 hertz in there. So what we can do, the next thing we would do is we would now filter those frequencies in the parametric block. So if we look at the parametric, what we actually did, rather than going back and putting notch for notch in what this one did, and these, you'll notice these go down to, 12, 13 dB of drop. We'll go over here and you'll see we just kind of drop in about 5 or 6 dB, just enough to kind of soften those frequency ranges. I say this over and over, use as little processing as possible on this, just because you can do it doesn't mean you should, because it could create bad outcomes there. Then what you can do is you can either have that notch feedback controller in there, or you can put it in a set of test tools and just probe in and out of it for each of your mics. You don't need to put one in for every single mic that you do. I would recommend using it just as a test tool. So, but what you do is you clear your dynamic filters back on the notch feedback controller, and then wait and see, is the microphone going to feed back? Go through some speech with it. And then when it no longer engages you can move on to the next problem mic in the chain. We had a question in there, Coy. Did you able to grab that one, or is it something we need to?
Yeah, I was typing a response to it.
Oh, perfect. Okay, just wanted to make sure. Didn't want to get too far down the highway.
No, you're good. They've been trickling in, but they.
Okay, perfect. Well, good. I'm not distracted by them, so I'm glad you're there. So the next thing we're going to talk about is mixers. So we kind of gone through EQing on the front end there, right? How you would EQ your mic sources. If you have, line level sources that aren't microphones and things like that coming in, you can certainly add a little bit of processing to those if you need be. Typically, I just put a little bit of dynamic processing in there to maybe a compressor or something so that it doesn't overdrive the input. But two major mixer types that we see a matrix mixer, and in Q-SYS we use a matrix mixer. Standard mixer, other, whatever it is, but that comes out of the inventory as an 8-in, 8-output mixer in mono, and you can reconfigure it. But the standard matrix mixer is the user assigns what signals go where, and the output is simply a matter of what all is mixed to that output. But when we start talking about auto mixers, they're designed for, to manage multiple microphones in a system and require no operator. So they actually, all the mic inputs get mixed to a common output. And then you have optional direct outputs that will contain only that corresponding mic signal, and those can be set up to be pre or post gate. Two major algorithms will decide which mics pass to the outputs, and we'll talk about that in the middle. The output level should remain constant though, regardless of the number of open mics. That's the tricky part. I mean, I even go back and think about the old, SCM Shure mic mixers that were you would set your priorities on the back. And the whole idea there is that when you're doing, whether you're doing voice lift in a room from a dais or something like that, or a panel of microphones, or you're doing conferencing, is that you always, no matter how many microphones are open and ungated and talking, you want that level going to there to be consistent. Let's talk briefly about the matrix mixer. There we go. So it has cross-point controls that allow you to adjust the relative gain, assuming that all inputs are adjusted to nominal. So if you've done your work, this is a key error that this is the first thing I will open up if someone sends me a file, is I will open up the matrix mixer that's mixing, the gated mics together and the program level and all that. If I see just all kinds of crazy adjustments here on the input and all in the cross points, then my first thing is I don't believe that the input gains have been set properly. Because if all your input signals have set properly and you're only running them through some dynamics and then getting there to the matrix mixer, you shouldn't be making large gain adjustments there. So that's something to look at there. One thing to note: all cross points come out of the when you bring this into your design, they all come out at -100, so you can in order, you have to set each one. They're not by default routed to each input to each output. So they can also, you can have mutes be enabled on each of those and route and unroute without changing the gain. So that's a configuration option in there as well. Auto mixers are used for conferencing and speech reinforcement. They have an adaptive threshold. We have an adaptive threshold gating on there. Maximum number of open mics is a suggested, is NOM, max NOM stands for maximum number of open mics. And the range on that is 1 to 3. So typically, this is rarely, if ever, do we need more than 3 microphones open at one time. Even if we have a large space or something like that, typically if there's that many people, you know, we've gone past a meeting and we're into an argument at this point. So, so we recommend a max NOM between 1 and 3. And that's where we do. The more mics that are open, the more harder it becomes to manage feedback and also the noise floor and all of that. You'll notice also on here that there is a manual button. And this allows for you the channel to be removed from the auto mix logic and excluded from the number of mics, open mics. So maybe that's the person that sits at the head of the table and you always want their mic on and you don't want their mic be affected. You can select those mics to be manually on there as well too. So something to know about that. So what we have here with a gating automatic mic mixer is with one mic open, we have no attenuation. So if you look over here on the right-hand side, you'll see that we have no attenuation that's happening there. Now, yeah, we have max NOM of 4, but it's only for these slides so that we show you, because I previously just said 1 to 3 is the greatest you should have. But the 4 is there intentionally for a reason, just to kind of show you how the auto mixer works. So when we add in a second microphone, what we actually start doing is we start reducing the output value of the mix output of these microphones, right? Because as those 2 signals add together, you get a larger signal in the output there. So with 2 mics open, the gain is attenuated about -3 dB to maintain that constant output. When we double the number of open mics to 4, the auto mixer would apply 6 dB of attenuation to maintain a constant there. Like I said, typically what you'll see is between 1 and 3 based on the room and size and how it's configured. The gain sharing auto mixer, I typically, for most conferencing applications, 99.9, I typically use a gating auto mixer. The gain sharing auto mixer, in my purpose, in my workflow, is used for live microphones that are actually being, you know, voice lifted or something like that into a room. And they just operate a little differently. So the way that it works in this one is there's a set amount of gain that can be given to the output. And so what you have here is that's a static resting point of it, right? So every one of these inputs is at -30 dB down because that's what it's set. The depth is set to -40 and the resting gain is set to -30. So it's just resting there. And then what you're going to see is as microphone 1 starts to talk, they will be given all of the mixer gain. And then as you add more microphones talking, so here we have, you know, 3 to 4 people talking, they're sharing that gain amongst them, hence the name gain sharing auto mixer. So that's kind of the way it works out on that one. Like I said, this one, typically I use a gating auto mixer for all of my conferencing. But, you know, anytime you're 8 microphones and below, you could potentially experiment with the gain sharing auto mixer and see if it gives you a little better performance. Every room is a little different. The reflections are different, all of that. So it's kind of hard to have a hard and fast on that. We give you a lot of tools to play with. So when we put it all together, we often need both auto mixers and we need matrix mixers in the same signal flow, right? Here's a few things. There should be no user controls for microphone levels. You'll notice here that in the center here, we have user program level. So we're bringing all our mics in. They're going through our mic EQ, and then they're coming into the microphone auto mixer. So the microphone auto mixer is going to give us a single channel out that we can, or you can get individuals and mix them inside of the matrix mixer as well too. But then you're going to go into a matrix mixer where we're going to take any program audio that's in the space and we're going to mix that together with the gating automatic mic mixer, then go into parametric EQs and then peak limiters to go out of our line out. So compressors, microphone dynamic processing. So these will level off loud talkers. They can be aggressive for spoken word sometimes, less aggressive for a vocal performance, right? So the problem or the drawback with a compressor is it does nothing to compensate for any quiet talkers, right? So it's typically for someone that's very dynamic in how they talk, or if you have a conference room or microphones, you may want to have a compressor in there. So if you do get a loud talker in the room, it's going to compress that audio down and do that. Automatic AGC, automatic gain controls, will help for quiet talkers, will also help for loud talkers. It operates a little bit slower than a compressor, and if it's not set up properly, it will actually keep increasing the level based on noise. So this one's this is a tier 2 component. If you're not super, if your DSP chops aren't up there, I would try to stay away from the AGC because it can cause more problems than it can solve if you're not really good familiar with it. One thing, never place gates ahead of an auto mixer. I'm going to be honest, I did this early on in my conferencing career. There was one microphone wire that was noisy, and it would always gate the gating mixer on, and I'm like, I'll just put a gate below that, but it obviously doesn't perform well. So it's a bad way to solve it. I should have solved that problem upstream from between the microphone and the DSP. When we introduce AEC to our system, this is a very basic AEC system. I wish if they were all this easy, it would be much easier to deal with. But what you have here is you have your mics coming in, they go through our echo canceling block, and then they go out to the gating automatic mic mixer and then out to your conferencing, right? Or they may hit the matrix mixer where you'll add program audio and some other stuff in and then go out to the conferencing output. The path to the near end for when we're listening to the far end is you bring the audio in from the VoIP or the USB or whatever the case it might be. That'll run into your mixer, and then you'll go out to the loudspeakers in the room. You'll notice that the reference tag there is actually right before the output going out of there. So what you want to do is you want to be able to feed a reference back to the acoustic echo canceller that is whatever is coming out of the loudspeakers. I always tell folks that microphones are, they're dumb devices. They're a diaphragm that when air hits it, it moves back and forth and creates an electrical signal, right? So it doesn't know whether that's your voice and it's supposed to reproduce that, or if that's the sound coming out of the loudspeakers, which if that happens, if it doesn't subtract that out of there, that is sent to the far end and is perceived as echo, right? So echo canceling allows us to do that. So what we do is we take this reference of what, the far end audio and any program audio in the room, and we attach that reference back to the echo canceller, and it says, oh, these are the things that I don't want to pass through. I want to subtract those out of. I want to cancel those things out of this microphone signal that's coming in. We talk about latency when we talk about AEC and all of that. We have our old algorithm in here, but it's really not relevant anymore. But the AEC does need some look ahead time. So on the Core 110, the 8 Flex, the Nano, that is 21.4 milliseconds. All the other cores, I guess at this point, would be the 610 and whatnot. It's 10.7 milliseconds on there. Tail length is an important thing to talk about. The latest possible, the tail length is the latest possible reflection that can be canceled, right? So basically, I explain it to people in layman's terms of it's how long the echo canceller is listening to reflections in the room before it does its subtraction process. Because if it was simple as, hey, I have a microphone here, and when the sound comes from the loudspeaker, the far end voice, it's going to have one direct path and that's it. But that's not it. That sound's going to hit the wall behind me and then bounce into the mic. It's going to come off the desk and hit that mic. So that's why we have to listen for longer times. Now, the tail length of Q-SYS cores are all advertised at 200 milliseconds. And that is pretty much the industry standard for most conferencing DSPs are going to be right around there. But in the Q-SYS platform, we give you the ability to be able to raise that tail length for more reflective rooms or larger spaces, and also decrease that tail length if you're in a very well-treated acoustic environment. Maybe I've got a microphone right in my mouth, things like that, on a gooseneck or stuff like that. So when you see, for instance, a Core 110 is advertised as having 16 channels of echo canceling, that is at 200 milliseconds. If you go to 300 milliseconds on all of your AEC channels, you would end up getting 12 channels of AAC. And then if you go to 400 milliseconds, you only get 8 channels of AAC. So I always like to be very transparent about that. And then I also like to mention that at 100, you can get 24 channels of AAC, but I wouldn't spec or design a system that way because, like I said before, that is like a small huddle room that's acoustically treated and the microphone is in very close proximity, things like that. So, but when you adjust it, adjusts the length of the FIR filter. The longer the tail length, the more DSP resources that are consumed. It takes time to do that. Conferencing terminology. So reference to microphone level ratio. So this is the difference in level between the reference signal that's coming in and the resulting signal that's at the microphone. So, you know, as our microphone is here, that signal might be coming into the algorithm at -30 dB, and our reference that we're putting in is at -20. So it's expressed as a loss. So it's RMLR, and we're going to be looking for -20. So with a -20 reference signal and a -30 microphone signal, we end up with a 10 dB RMLR. This is also known in other platforms as echo return loss. Residual echo suppression is the same as nonlinear processing in other platforms. And what this is going to do is we talked about tail length. What this does is after the 200 milliseconds has gone on there, if there's any additional artifacts or anything like that, it will, after the FIR filter has done its job, it will snip those little pieces out of there. So voice lift, that is in larger rooms where we need our near end microphones to not just be sent to the far end of the conferencing, but also to the loudspeakers in the room. Voice lift, in my mind, is not the same as public address PA type audio, right? So if today I'm coming to you from the training room at our Austin Training Center, you know, I might in the back row of the room here, I might put a small portion of my microphone voice audio into that back row so that those people can just get that little bit of augmented voice lift there. So it shouldn't sound like Sunday at the Monster Truck Rally. And so many times customers will be like, well, I thought my voice was supposed to come out of the back. Hello, hello, I don't hear it. But if you go sit in the back of the room, you know, typically just have them sit in the back of the room and you're like, see, I can talk in a normal voice and you can hear me quite clear, right? And that's kind of what we want to do. Mix minus is a completely different situation. You know, mix minus is where you might have a large conference room and you have a loudspeaker zone, whether that's, you know, right in front of them or above each microphone. And what you'll do is you'll mix, you'll take microphone signals, say that are at the front of the table, and at the far end of the table, the opposite end of that table, you'll, you know, add maybe 6 or 9 dB of that mic into the loudspeakers just over that head. And as you get closer to the mics, it will taper, you know, 6 dB, 3 dB, and then anything within 6, 8, 10, 12 feet of the end of the table would be, you know, it would be a 0 dB add of that microphone to the loudspeakers there. So that's used sometimes once again, this is a little more complex setup type situation. But when we look at our path to the far end, we have our local microphones, we go through the AAC, and then we do our gating automatic mic mixer, and then we go out to our conference. On the near end, I kind of walk through this one, we have our program sources up top, and then we have our VoIP and soft phone, could be USB conferencing, could be, you know, analog, whatever you want it to be, could be coming in there. So typically we find that we apply our equalization between the acoustic echo canceller and the gating mic mixer. You best practices say do not do any dynamics between the microphone inputs and the input to the echo canceller. We want that to hear as clearly as possible of what we're seeing in there. Best practice, apply all of these after the AAC algorithm. And you'll see inside our channel group here, we have a high pass filter, a parametric, a low pass, and then maybe a compressor. So key takeaway from here, there are maybe times that you need to put a high pass filter to get like some low end rumble out of a ceiling mic or something like that prior to the echo canceller. Those can happen, but definitely don't put any of your dynamic stuff like compressors, limiters, any of that prior to the echo canceller. Oh, there we go. I didn't know there was a slide that said that. So no nonlinear objects should go ahead of the AAC. So there is a never section. The most important factor in successful AAC is in fact having the correct reference signal. When there is no voice lift, the adage is what goes to the loudspeakers goes to the reference. So all the far end audio, the program sources, especially if they're routing those to the far end, should also go there. Never put a microphone signal into there. If you hear an underwater sound, or if the far end says they hear an underwater sound, you probably have added a microphone to the reference there. So, because what's going to happen is instead of when it's trying to subtract the program audio out, if you put the microphone reference in there, it's going to try to cancel that out. So it's going to sound really garbled on the far end there. So assuming you've already brought all your microphone signals to -20 DBFS nominal and are achieving at least 15 dB of intelligibility, the thing you're going to do is set your amplifiers to a minimum level or set the output block max RMS gain to -40 dBu if there's no controls on the amp. Using the preamp analog gain to bring all the program sources up to -20 dB full scale nominal. So you want to do that on the output, and then leave all your program sources at unity gain. So you want to just leave those coming straight through, right? With calibrated program source, what you'll do is you'll play a program audio source. I don't recommend doing it with a mic because that varies, right? So once you know you've got a test tone or a speaking track or something that has a constant level or fairly constant level, that calibrated input, you'll start bringing the volume level up on the amplifier or the max RMS setting up till you get to a typical listening level. Typically, this is about 70 dB. Now, I've been told, and early on in my career, I was told that the human voice average is about 65 dB. And I would always set my conference rooms up when I was balancing them for that to be at -65 or at 65 dB. And then I found that most people hit the up button about 2 or 3 times and increase the volume. Typically in a conference environment, people want to hear 3 to 6 to 8 more dB than what we're normally used to hearing, right? So while my human voice when I'm talking to you person to person is about 65, in a conference room, you want that value to be at 70. Then you make a test call. You adjust the far end gain to nominal receive level. So when the far end's talking, have someone on the far end of the call talking into the room, you want to adjust that gain because that gain's just as important as the microphones because we're mixing all this stuff together and we're coming out of our own loudspeakers and some stuff we send to the far end. And also when the listener, with the listener at the far end, the AEC can be fine-tuned as well. Apply only enough noise reduction to remove the steady state noise in the room. So you've got noise reduction over here on the bottom right-hand side. And the RML target is going to be 0. So you're going to want this reference to microphone level. This is the easiest meter in Q-SYS to read. When it's bright green and in the middle, it's right. If as it goes down or up from the middle, it will go yellow or red. And then the noise reduction is for steady state noises. It's not going to, if Bob, the loud talker, has an office next to the conference room, the noise reduction isn't going to take Bob, the loud talker's voice out of it. It's, it's going to be that projector fan or something, or equipment rack noise or something like that is what you're going to take out with that. If the RMLR meter is not green, reduce the reference gain until it drops in increase or decrease. There is what you can do on that as well. The adaptive filter up top is when you can't mute the microphone after the AEC when you can't mute the microphone after the AEC, say you have to mute it prior to the AEC for whatever reason. The adaptive filter helps it recover faster and reconverge its algorithm because it kind of fakes the circuitry out and kind of simulates what the actual noise floor of the mic is. So what you do on that is you just put the microphone in the space, you listen to it, you just be quiet and listen to your input, look at your input gain. And whatever that value is sitting at, so if it's at -53 or 57 or whatever, that's about where you'll start your adaptive filter. So you'll set it there. And so the idea is when you mute the microphone prior to the echo canceller, which is not best practice, but sometimes unavoidable, if you mute it prior to that and then unmute, there shouldn't be any 15-20 second lag of convergence time that needs to happen there. So that's kind of how you set that up. All right, so RES, so residual echo suppression. This sets the nonlinear processing after the algorithm finishes. Increase if there is residual echo in your system. But the more of this residual echo expression you ask, the closer to half duplex you'll get. So you'll end up further away from a two-way conversation and more of a walkie-talkie type conversation. Depending on who your conference is with, that might be a good thing, right? When you're talking, you don't have to listen to them. So anyways, I say that tongue in cheek, but and then this is also where you want to test your double talk condition. And double talk is if people on the far end talk and you talk at the same time, is it clear for both opposite directions, right? So if that's the case, if I'm sitting here talking and I'm clear on the far side, but someone else on a bridge call or something talks and my voice gets garbled, then we have too much residual echo suppression in there too. So that's another key indication you've added to. What if there's still significant echo? Well, make sure that your signals aren't misrouted or looped back in. This can especially happen. I've seen some video codecs back in the day when we did hard codecs that, you know, depending on which output you used, it may not have, it may have some stuff in it that will cause it to loop back. And what I do is just go through and mute your microphones, verify, is it really echo or is it direct coupling? Have I miswired something inside of the design? If the echo is still there, then mute the inputs until you've identified what source is routed and then move forward. What if there's still significant residual echo? Well, this looks like a great thing to do. Then you should treat the room with this to be an anechoic chamber here. So now actually check your tail length. If you had it set to 100, which I don't recommend starting there, you could extend it to 200. If it's at 200, the immediate result, most people, if you have echo and it's a standard size conference room, I mean, the 300 and 400 just doesn't fix everything. Oh, well, I just need more AC. The 300 and 400 setting are for those, you know, 2-3 walls are glass. It's a marble table. It's a concave hard deck ceiling above the table. And there's just, you know, tons of reflectivity in the room. It's a really big space. But if you can't get the echo down with using the tools that are in there, you may have to recommend things to do it. So then when we set up, what you do is you'll go through each conferencing type. So typically in today's systems, we see primarily we'll just see a, you know, just a USB type input for conferencing. We may see VoIP and USB. You know, in the old days, we used to have VoIP, video conference, and then maybe even POTS line as well too. But the idea is you're going to go through each conferencing type and do a test call testing all of them. You know, don't just start with the lowest common denominator, which is a POTS line call. And well, if this one sounds good, they'll all sound good. You really want to test each one. Then typical design elements that you post afterwards, you know, you'll go through your gating auto mixer and then your program, and then you come back out and you've got your output signal conditioning. So this parametric EQ would be what you would use to go out to your loudspeakers, or maybe if you're going out to a recording device or something like that. And also the peak limiter is in there as well. Post mix EQ in the output signal chain is typically for a speaker EQ. So you can use the curves recommended by the speaker manufacturer. If you're using Q-SYS speakers and you're using either our analog or our digital amps, you can use the intrinsic correction blocks in there. So we've already given you a block that if you're using our loudspeakers, in order to make them flat, meaning they reproduce as closely to as accurate as what we see, then we're going to, you know, what signal gets put in and gets reproduced as accurately as possible. So that intrinsic correction, we build that in for you. But speaker manufacturers will publish what the recommended curves are there. So that's what you would want to do on that output side. And then there's also, you're going to do a little bit of room EQ, right? So every single room is going to react differently to the sound pressure that's being put into it. So that's where, you know, if you've got extra reflectivity, you're going to notch some problematic frequencies out, stuff like that. User gain controls. Are user gain controls better at the input or the output side of the mixer? Well, the simple way to decide this is, does the user need to control the level of all outputs pre-mixer independently, or can you just simply give them one simple volume control and be able to raise that volume up and down in the room? Some school of thought says that if the room is properly set up and everything, you should really never have to touch the gain controls. Although, you know, a couple of, sometimes you end up in a call with a lower volume, you need to pump something up a little bit, but it depends system to system. So the idea here is don't give the user enough control that they can ruin the gain structure, right? So set reasonable upper and lower limits on the controls that you do give them. So output limiting. So limiting will prevent a signal from going beyond a predetermined level. So it'll help prevent clipping, prevents overloading of downstream devices, whether that's a recorder or an amplifier or something like that. The peak limiter blocks default threshold is 0 dB, but let's take a look at what's ideal when we use that. So below, you'll see that this is well below the threshold here, right? So my little fireball is well below the threshold as I'm talking. And if I go up to 0 dB, you can see that it overshoots that 0 dB and kind of drops back down by the time it actually reacts. So we end up applying a lot more gain to it. So one of the things that we like to recommend is if you set that down about negative, reduce the threshold by about 3 dB, this will provide an extra layer of protection to keep you from clipping downstream as well too. So it will just build a little bit more margin before the signal will actually clip off for you there. And then QSC amplifier limiters set automatically if speaker blocks are configured properly. So if you're using the speaker blocks, if you're using our digital amplifiers and you're using QSC speakers, you can simply drop these blocks in and they will know how to configure that amp. So it'll say, hey, that's a 6-inch in-ceiling speaker. It only needs maximum of this much voltage, this much current. But also you can put generic speaker blocks in and configure them for different types of loudspeakers, and you can still have the amplifier manage some of that for you. There are different types of limiting in the digital amplifiers. You have a DAC limit, which is your digital analog converter limit. So going from the digital world back out to analog, if it's going to clip in there, we're gonna clip at that stage. We're gonna prevent clipping at that stage of the amplifier. We have a protect that'll be due protect limiting. Whereas if we get a low impedance condition, maybe a short in the wire or a voice coil starts to fail and becomes a short before it usually becomes an open, that protection will do that. And then limiting will be computed based on the load type. So how many loudspeakers, what loudspeakers are there. So if you're not going directly down to a QSC amplifier, ultimately we must convert the digital audio and the digital sound processor back to analog. In this limiting example, we saw clipping at 0 dB full scale, as you would expect. In keeping with our 20 dB of full scale gain structure, the digital gain should always be left at 0, right? So we're still in the digital domain. We don't want to turn it down before it goes to the digital to analog converter. Just like on the front end, we wanted to give a good, healthy signal for it to sample. What you'll see here is at 0 dB of digital gain, my max RMS output level. See, this is one place where you actually see dBu because we're dealing with dB full scale in the digital realm. Once the signal goes through the digital to analog converter, then our meter up here is in dBu. This would be perfect if the downstream device is a professional audio device and it's looking for +4 dBu nominal and 24 dBu max. This is going to be right on, right? Because it's going to be right there at 24 dBu. What if the next device in line is a consumer level device? Well, let's take a look at that. Ideally, we want all the components in the chain to clip at the same point. So a consumer line level is going to be -8 dBu, right? So we want 12 dB of headroom. Assume the maximum input level of 4 dBu RMS. So now we reach +7 dBu peak at 0 dB full scale. So what we've done here is we've actually reduced the output gain after the digital to analog converter to make sure that the clipping point for consumer level device is closer to 7 or 8 dB. And so that's kind of where we're looking for there. We want that to be there. The output is calibrated for the downstream. Sometimes you do have to feed a microphone level device. Make sure this device doesn't provide phantom power because that'll damage our output circuits. But you can cut the level back. We have moved all the way back to -61 so that we're just barely, we're putting a very small signal out of this box to go into something that's looking for a mic level input. Output gain structure. So when you increase the output, when decreasing the output level will actually decrease the signal to noise ratio, right? So if the noise floor of that output is here and I'm able to go out at full +24 dBu, I have the most signal noise ratio that I have, the highest one. When I go down to a consumer line level, I have to bring that level down some. So now I have a lower noise, a lower signal noise ratio. And when I get down to microphone level, obviously I'm way more susceptible to noise there as well, because You know, if that noise floor is at negative, if our output card is at negative 80 and I'm at negative 40, I only have 40 dB there, or if it's at negative 60 or something like that. So just something to be aware of. So let's just review real first. The most important thing is to calibrate stuff on the input and adjust the analog gain to bring all the Q-SYS inputs into the system at a negative 20 dB full scale. I have to admit, when I first came to QSC and started using the cores and whatnot, I went in and set all of my mics to 0. And the first test call I made, I'm like, oh, it's horribly overdriven. What's going on? And then I realized those meters are in dB full scale. So microphone equalization. So we trim the high and the low frequency noise with low pass and high pass filters. You add a parametric to put suggested curves in there. You can also use it to notch out problematic frequencies. And you can also use one of our notch feedback controllers in there to identify what frequencies are causing the feedback. And then you can add some dynamics after that. Some automatic gain controller compressors can be used to get consistent levels from your talkers. And then you have auto mixing. So then we're going to go through them there. Never place level controls or gate end user level controls or gates ahead of your auto mixers, and use gating auto mixers for noisy rooms or rooms with 8 to 12 microphones. One thing to constantly remember, use the fewest number of gain controls possible to get the job done. Avoid multiple controls in the same signal path. It's going to end up ruining your gain structure. And then output limiting. We want to be able to limit the output of the signal depending on what the downstream device is. If it's QSC amplifier, that's already going to be done with the blocks that you would tie to it. If you're doing an analog amplifier or some other downstream device, use a peak limiter component to do that and set those things up properly. And then you set your output calibration. You want to make sure that the room has the ability to be able to that the output level into the room is around 70 dB there, so that it's just a little bit louder than the average human voice. So, any questions for us? I will tell you, you will get. We have a nice little handout that's it's a practice that'll be sent to you that talks about all of these steps. I call it the placemat. So it's about it prints really nicely on 11 by 17. So it's a really good guide that walks you through this. And then on the back side of it, it talks about some best practices with AC as well. You'll get a copy of that emailed to you. Plus, you'll get a link to take the 8-question assessment, and you can pick yourself up an extra half RU of VIXA renewal credit. So, any questions from anyone?
Yeah, we got one here, Dan. I was going to reply, but I figured I wasn't quite sure what he's asking. So Travis asked, can you talk about using Q-SYS loudspeakers, speaker processing blocks, but making additional EQ, high pass, low pass adjustments? Looking for best practices. So I'm not sure if he means in addition to processing with those additional EQ, maybe where to place those. Yeah.
So Travis, what we'd actually be looking for there is, yes, you could certainly, I mean, that intrinsic correction block, it does a couple different things for it. So on the Q-SYS amplifier, if you're doing a digital amplifier, it ties on to the output of that. And what that does is if you say, hey, this Q-SYS, these ceiling speakers are set to 70 volts, it will automatically configure the amplifier for 70 volts. It's going to set up all the limiting, and it's just going to add the intrinsic correction to flatten the speakers. But by all means, you would still put some room EQ tools prior to that. So you might have a high pass, a low pass, and a parametric in there to be able to do some of that. So hopefully that answers the question. If not, pop me back as well. So, okay.
We had one more here.
Okay, cool.
He's asked, if you have a Dante mic source and Dante amp output, setting unity gain would be modifying the digital gain to negative 20 DBFS, and the output gain would be left to the default the block is set at consumer pro levels, and then gain down the amp and go from there.
So we have Dante mic sources,
and
Dante amp outputs, setting the unity gain would be modifying the digital gain. Yes, so whatever that, yes, in this case, since we're not going to leave, I think I know where you're going with on this one. So yeah, if I'm bringing Dante mics in, they need to hit 20 dB, negative 20 dB full scale. If I'm going to a downstream, if I'm going to a Dante amplifier, so if I'm going out a Dante card, I'm going to want to do the same type of situation there. So the output gain, I wouldn't leave it at default. I would make sure that it's setting, looking for that unity gain to go down to the amplifier on the downstream side. So you still want that head for, at this point, think about it, you're still in the digital world, right? So, but I know there's a software Dante block or a hardware Dante block on the output. But yeah, you want
those gain settings are different in that block. Just kind of going back to your initial question, just like on the input side, the output side doesn't have an analog trim on it. It's just a digital gain. So there's fewer places to go and screw that up. It's not there because it wouldn't apply to this, because we're not converting it back to analog. It's staying digital all the way through.
And for those of you that saw my screen, I know that it's not just a logo, it's sometimes a performance rating. So for any of those Cowboys,
Glad to be a Cowboys fan.
So, anything else? Well, cool. Well, great. Well, thank you everyone for this investment of your time. We certainly appreciate it. And yeah, actually looking forward to seeing you all on another one upcoming soon. So take a look. I think at the end of the month, we have a what's new in 9.7. So if you know 9.7 release this week, so you may want to download that and look at some of the changes and things that are going on with it and go from there. So nice. Coy got a little props on Oscar there. We're still trying to come up with a name for Coy's stash. So. All right. Well, everyone have a great day and thank you very much. We appreciate it.
Thanks, everyone. Have a good week.